Welcome to lesson 3 for chapter 8, parametric equations. This is year 2 pure mathematics, and in this lesson we're going to look at how to solve some coordinate geometry problems involving parametric equations, which we've been looking at in the first 2 lessons. So that pretty much sums it up really. I'd like you to pause the video and try the 4 warm-up questions, please. Okay, and now let's have a look at the solutions. Okay, so the first one, we're just going to introduce some simple ideas that you're familiar with. We have parametric equations defined as you can see, and t, the parameter, is valid for all real numbers. So that's good. When we set x equal to 0, as in part A, obviously that's going to find the y-intercept of the curve. And for part B, when we set y equal to 0, clear that's the x-intercept. So you can make a note of that if you want. I'm just going to put it on here. So obviously this is the y-intercept. And when y equals 0, this is the x-intercept. So we don't know how many there are. There could be 1 or 2 for each or more. We don't know. The way we do that is by solving the equations. So for part A, we just set x equal to 0. So if x equals 0, then t plus 1 equals 0. Okay, because that's how t is defined. This will give us a parameter value of t that we can actually use. So that means that t would equal -1. Now, because t is equal to -1 in this instance, where there is a y-intercept, that means that we can actually figure out what that y-intercept is by subbing the t equals -1 back into the equation for y. So we could put the t equals -1 back into here, and that would return us the y-intercept. Okay, so the actual y value itself. We're not asked to do that, but that's just something to be aware of. Now for part B, we have to find when y equals 0. Well, when y equals 0, what happens? Well, we set the equation for y equal to 0, obviously. So that's going to be t subtract 2 all squared is equal to 0. Now, if we take the square root of both sides, okay, obviously the square root of 0 is 0. So we get t subtract 2 is equal to 0. So t is equal to 2. Now, even though that was squared, at any other point, we would probably expect there to be 2 solutions to this, seen as t is any real number. But once again, if we take that value of t equals 2, and we sub that back into the x equation, we would actually find the coordinate of our x-intercept. So if this goes back into here, when t equals 2, we could see that the x-intercept is when x is equal to 2 plus 1, which is 3. Okay, so just be aware of that. Now for question 2, we have a curve C with parametric equations, and notice that it's x equals sine t, y equals cos t. So this is something we've looked at already. Only defined for acute angles, but including pi over 2 as well, which is 90 degrees. The line y equals 1 intersects the curve C at the point P. So we have to find the value of t at the point P and hence state the coordinates of P. Well, it's a bit of a mouthful that. If we are interested in points of intersection, so obviously we're leading into geometric reasoning here. The line y equals 1 intersects the curve C. Well, if y is equal to 1, that fixes our y value. Okay, now in the parametric form, that just tells us that this y value here must be equal to 1. Okay, it's literally that simple, isn't it? That's all it's telling us. This must be equal to 1. So if we set cos t equal to 1, that will give us the value of t, and then we can hopefully deduce what the coordinates of P are. So let's do that. So from what we've just said, we solve cos t is equal to 1, and we're taking the range of values of t to be up to and including pi over 2. Well, when is cos t equal to 1? Well, obviously that's when t is equal to 0. Okay, that's from the cosine graph. Okay, and just as a point of reference, we could just sketch that cosine graph as well. So the one we're talking about, just simply between 0 and pi over 2, we know that cosine, if I put this on here, so I'll put that as the t-axis, we'll put that as the y-axis. If it's cos t, it starts at the maximum and plunges down to 0. So that maximum value, of course, is at 1. And this is y is equal to cos t. Okay. So there we have one solution. Now that means that t equals 0. What does that tell us about the x value? So given t is equal to 0, we know that x would equal sine of 0. Now sine of 0 is of course 0. Right, which means that we've actually found the coordinates of P. So we now know that at P, x is equal to 0 and y is equal to 1. All right, now, or in other words, P is at 0, 1, with the parameter t being, of course, 0. Now, we could also think of this a bit differently. If we know, for example, that we've got x equals sine t, y equals cos t, we know that the Cartesian form is just going to be simply x squared plus y squared is equal to 1. But of course, we're only interested in t values between 0 and pi over 2. So that would just give you a quarter of the circle, essentially, which is the same quarter as we've got on this graph here. You can think of it like a circle. So it's just the first quadrant, essentially. Now, that would mean that if that intersects with the line y equals 1, indeed, that would be, of course, at the point 0, 1. So I'll just show you what I mean on a diagram. So if we just draw that, x and y, so it's a circle radius 1, but of course it's only defined for the first quadrant. Okay, so x squared plus y squared is equal to 1, radius of 1, of course, center at the origin. And if we put the line y equals 1 on there, it's going to be a horizontal line that intersects right there at the point 0, 1, which was what we've just deduced. Okay. Now that would be using the Cartesian form. As you can see, it's quicker and easier just to use the parametric form. Now for question 3, again, the domain is going to play an important role here. So we notice that f of x is defined as a quadratic. It's in completed squared form, but we have this domain here between -1 and 0, and not including -1 or 0. So a good idea, again, would be to sketch this. If this was just all real numbers, we could see that the maximum value would occur, of course, when we have a 4 there, because you're subtracting square numbers and they're always positive. So if we just sketch this function, we can see a few pieces of information before we do. There's a mirror line. So if we set x plus 1, which is inside the bracket, equal to 0, that gives us the equation in the mirror line. In other words, x is equal to -1. Okay, so there is going to be a maximum there's going to be a maximum point at the coordinates -1, 4. Okay, now -1 is on the boundary of our domain. Okay, so it is valid, this. Let's see what happens elsewhere. So we'll just sketch what we know first of all, and then see what happens. So my domain is between -1 and 0. We know it has a maximum of 4, so I'm just really interested in that top left quadrant. Okay, so we'll just label all this. So y, 0, which is the origin, and x. So between -1 and 0, we're going to go, let's say, from about here. The 0 is the origin, of course. And we have a maximum at 4, which will be up here. Now, we also know that at -1, that's where the mirror line is. So at this point, -1, 4, that's where we have the mirror line. So it's the right-hand side of this parabola that we're interested in. Now, at the point where x equals 0, we really need to find out what the curve is doing. Okay, so we've got from -1 to 0, but what is the curve doing at x equals 0? Well, you just have to sub in x equals 0 and find out. So when x equals 0, what do we have? Well, we have f of 0 is simply going to be 4 subtract 2 lots of 0 plus 1 all squared. In other words, it's going to be 4 subtract 2 lots of 1 squared, which is just 1. So 2 lots of 1, which is 2, and then 4 subtract 2, which is 2. So that gives me a y-intercept at 2. So my parabola is a bit squashed on my diagram, but there is a maximum here, and it's going to be curving down like this at 2. Okay, and it will cross the x-axis somewhere over here, but I'm not particularly interested in that. So what does this tell us about the range? Well, we've got it right in front of us now, so we can see that the range is going to be between 2 and 4, and neither of those values are going to be included because -1 and 0 are not included either. So we'll just state that. So the range, I've made the assumption, of course, that x is a real number in this. So x will be bounded between, sorry, I beg your pardon, y will be bounded between 2 and 4. Okay, according to the sketch. Right. Now, moving on to question 4, we have an equation with a k as a constant, and it has 2 distinct real roots, and we have to show this inequality. So this is going back to our work on discriminants from year 1. So looking at our equation, what do we know about it? Well, let's just write it out and we can deduce a few things. So we have x squared plus kx subtract k. Now, in order to use the discriminants and the quadratic formula, you have to have your equation in the form, which I'm going to just write down. And it's really important, this, because it's often overlooked. Ax squared plus bx plus c equals 0. And it's the right-hand side which is absolutely key to this. It has to be set equal to 0. Okay, so I have to subtract 1 from both sides in order to continue this question. So if I subtract 1 and then set that equal to 0, we're now in business. So in this situation, let's see which corresponds to which. So we have a is the coefficient of x squared. So I've got nothing there as such, but we know that that represents a 1, doesn't it? So I'll put a 1 in there just to acknowledge that. My b plus b, of course, that's going to be plus k. That's fine. And then the plus c. So this is where we've got to, again, be careful with signage, or signs, I should say. So the plus c corresponds with the negative k subtract 1. So let's write down what a, b, and c are, and then we can use the discriminant. So A is going to equal 1. B is going to equal K. And C is going to equal negative K subtract 1. All right. Now, if this has two distinct real roots, we know that B squared subtract 4AC must be strictly positive to create those two real roots. So let's do that. So we're going to have K squared, so that's B squared, minus 4, lots of A, which is 1, multiplied by C, which is minus K minus 1, is strictly positive. Okay. Let's tidy this up now. So we have K squared minus 4, and then I'm just going to put the minus K minus 1 in. The A is 1, doesn't really do anything. Okay, now we have to multiply out the bracket. So therefore, K squared plus 4K, and then negative times negative is, of course, positive, plus 4 is greater than 0, as required. Okay, so that concludes the warm-up. All right, so let's start doing some coordinate geometry with parametric equations. So we're given the two equations, and for part A, it asks us to find the coordinates of the points where the curve meets the coordinate axes. So straight away, there's some prior knowledge that we need to retrieve here. The curve meets the coordinate axes. Now, obviously, where the curve meets the coordinate axes, there's some key information we need to write down. So, i.e., coordinate axes, well, it's when x equals 0, that's the y-intercept, and when y equals 0. So we'll just make notes of those. So when x equals 0, that's the y-intercept, of course, as I just said, and when y equals 0, it's the x-intercept. So those are the, and I can't spell it, so x-intercept. Okay, and there may be more than one of each or none at all. All right, so if we set x equals to 0 for part A, let's see what happens first of all. So when x equals 0, what does that tell us? Well, it tells us that t plus 2 must equal 0. In other words, t must equal negative 2. And now we have that information. This value is really important because this tells us the parameter, the value of t when the y-intercept occurs. Okay, now in order to get that y-intercept, we have to find the exact coordinates. We now need to sub that value of t into equation 2, which I'm going to label now. So we'll call this one equation 1, and we'll call this one equation 2. And we're going to sub this into sub t equals negative 2, which we've just deduced in equation 2. And I'll do that in red just to make sure it's really clear. Like so. So it's all factorized nicely. Let's just plug it in. And then we get the Cartesian coordinates for the y-intercept. So y is going to equal t, so that's going to be negative 2. So I'll just put that in green. Negative 2, subtract 1. Close that bracket. And then we have 5, subtract 2 lots of negative 2. So we've just got to be careful with the signs here. Close both those brackets. Just plugging it in. You could expand it if you wanted to. So therefore y is going to equal, that's going to be negative 3 multiplied by 5. Now negative 2 multiplied by negative 2 is obviously positive, so that's going to be plus 4. So therefore y is going to equal negative 3 multiplied by 5 plus 4, which is of course 9. So therefore the y value at the intercept is going to be 3 lots of 9, which is negative, so that's minus 27. Okay, so there's only one y-intercept, and we know this because we only discovered one valid value of t when x is equal to 0. It's not always the case. Okay, so we'll just write down that pair of coordinates. So the y-intercept occurs at 0, negative 27. You can check this if you plot these parametric equations on some graphing software. You can do that. You'll be able to see that. Now for the rest of part A, we've also got to find out the x-intercept. So we're going to set y equal to 0 now. So y is equal to 0. What does this give us? Well, it gives us a nice factorized quadratic, first of all, equals 0. Now, this is definitely going to return 2 possible values of t. And remember, of course, t can be any real number, so that it's all going to be valid. So therefore, t minus 1 is equal to 0, or 5 subtract 2t is going to equal 0. So in other words, t equals 1, or t is going to equal 5 over 2. So there are 2 possible x-intercepts in this situation, when t is 1 or when t is equal to 5 over 2. So when t is 1, so let's find out what that is. So when t is equal to 1, what happens? Well, we just sub into the x equation. So just make a note of that. So sub in equation 1. All right, so what's that going to give us? So that's going to be x is going to equal t plus 2. So that's just going to be 1 plus 2, which equals 3. Okay, so the first x-intercept is going to be at the point 3, 0. Okay, so that's good. And then for the second case, when t is equal to 5 over 2, obviously we're subbing in 1. X is equal to t, which is going to be 5 over 2, plus 2. Okay, now it's up to you how you write this. You can do it as decimals or fractions, it doesn't matter. But obviously, 5 over 2 plus 2 over 2 is going to give you 9 over 2. Okay, so in other words, 2.5 plus 2 is 4.5, which is 9 over 2, or 5 over 2 plus 4 over 2 is 9 over 2. So that gives us the coordinates 9 over 2 and 0. So we've managed to figure out quite a lot of information about the curves already, even though they're in parametric form. With a bit of work, we've now got the y-intercept and 2 x-intercepts. Now, we don't need to know anything else other than that. Now we just move on to part B. We're told that the straight line L passes through the points A and B where t equals 1 and t equals 0 respectively. Okay, and then we have to show that the gradient of the line L is 5. All right, so for part B, when at A, we know that t is equal to 1 because we've got that respectively, it means in the same order. So that means if you weren't sure about that, that means A corresponds to t equals 1 and B corresponds to t equals 0. All right, just so you're aware of that. So at A, t equals 1, so that means that x would equal 3. And y, now we've already worked this out because when t equals 1, we know that y is going to equal 0. And you can tell from the bracket because we put 1 in there, it's going to be, it's going to just knock out y. So that's going to be 3, 0. Okay, so we knew that already. So that's 3, 0. And at t equals 0, which is at b, so x is going to equal t equals 0, so that's just going to equal 2. And y, now if we put 0 in, we're going to have negative 1 multiplied by 5 subtract 0, which is just 5. So that's going to be equal negative 5. So that means we're going to get the coordinates 2, negative 5. Now, just to clear a bit of space, okay, so I've just cleared a bit of space on the left to continue B. I've written down the 2 pairs of coordinates for A and B. Now, to find the gradient of the line L, which connects these two points A and B, obviously the X coordinates correspond and the Y coordinates correspond. So this is a bit of coordinate geometry from year 1, isn't it? So I'll just label these points, so that we'll call this one x1, we'll call this one x2, and we'll call this one y1, and we'll call this one y2. I mean, you'll have your own systems for doing this. That's absolutely fine. So the gradient of L which we usually call M, don't we? So it's simply going to be y2 subtract y1, so the change in y over the change in x. So we have to show that this gradient is 5. So let's sub everything in. So we're going to have y2, which is negative 5, subtract 0 over x2, which is 2, subtract x1, which is 3. So this is going to equal negative 5 over negative 1, which does indeed equal 5 as required. All right, so by substituting in a few key values of t, we return to familiar coordinate geometry that you did probably in year 1 and perhaps even prior to year 1. Okay, now in example 2, we have parametric equations with an unknown constant a, which we have to find. And we're told some key information. We're told that the curve intersects the y-axis at negative 4 right here. So it's the y-intercept essentially. So let's just make a note of what we know. So the y-intercept now, if it intersects the y-axis at negative 4, we can write that down as a pair of coordinates. So simply going to be at 0, negative 4. And obviously, we know all about coordinates. This is the x value. This is the y value. So if we set x equal to 0, that might help us along the way. So let's do that first. So set x equal to 0. Now, if we do that, we get this interesting result. So we get a multiplied by 1 subtract t is equal to 0. And this is factorized. So that means either a is 0 or 1 subtract t equals 0. Now then, if a was equal to 0, then that would knock out the whole of the equation for x, which would just be 0, and the whole of the equation for y. So a can't be 0, okay, because that wouldn't give us an equation. It would just give us a point, which is the origin, which clearly does not cross the y-axis at -4. So we know that a cannot equal 0. So 1 minus t equals 0 must be the way to go. All right, I hope that's clear. Just common sense, really. If you put a 0 in, you just lose your equations. So in other words, that tells us that t must equal 1. So we've just discovered the value of our parameter at this y-intercept. Okay. Now we also know at the y-intercept, as well as now knowing that t equals 1, we also know that the value of y, that the y value is obviously going to be -4. So we're going to do that next. So we're going to set y equal to -4. And obviously t is any real number, so we don't have to worry about that in this situation. Now, when we do that, we get 2a multiplied by t plus 1 all squared is equal to -4. All right. Now, we've already established, this is, again, all factorized, but when we know a is non-zero, which must be true, because otherwise that would make an invalid nonsense equation. But we also know that t is equal to 1. So we know that t is equal to 1. So in other words, so therefore 2a multiplied by what would be 1 for t plus 1 all squared must equal -4. Now, we could probably divide by 2 here on both sides. So this would give us a multiplied by what essentially is 2 squared must equal -2. So in other words, 4a is equal to -2. So a must be equal to -1/2. All right. And that's all we had to do for that question. It's just deducing what the value of a was going to be. So for worked example 3, I'm going to show you 2 different methods for doing this. And we have to show that this curve defined parametrically by the 2 equations does not intersect this line y equals x plus 1. Something to bear in mind, obviously, you're going to show something does not intersect. And this goes back to some work you did on lines intersecting circles back in year 1. So we'll come back to that in a moment. Now, if you notice, if you want to show that 2 equations are intersecting, then you have to substitute one into the other essentially. Now, if the equation for the curve is valid when the line is valid, then obviously the x component of the straight line must correspond to the 1 minus sine t. So I'll just make an issue of this at the moment. So on the curve C, we know that x is equal to 1 subtract sine t. Okay. And also, we're given that y is equal to cos of 2t. Now, if that's the case, then, and this line does in fact intersect with the circle, then if I set up the equation, let's say for L as y is equal to x plus 1, we can actually sub. Now I'm going to call it 1 and 2 for the 2 parametric equations. What we can now do is we can sub 1 and 2 into L, because the equation for C has to be valid and the equation for L has to be valid. That's if they intersect. So we're going to show that they don't. Now, if we just assume that's the case, then if y is equal to x plus 1, then y I can obviously replace. So this y here I can replace with cos 2t. Similarly, the x on the right-hand side I can now replace with 1 subtract sine t. And that's exactly what I'm going to do. So on the left-hand side, sorry, I'm going to have cos of 2t and that's going to be equal to x plus 1. Now, x is, of course, 1 subtract sine t. All right, and then obviously there's 1 added on. Okay, so that, just to remind you, corresponds to y is equal to 1. Sorry, no. Y is equal to x plus 1. Right, so let's just tidy this up a bit. So we've got cos 2t equal to, now we've got 1 plus 1, which is 2. 2 subtract sine t. And we have another problem. We have the problem that we've got two different variables. We have the variable t here, which is having the sine function applied to it, and 2t here, which is having the cosine function applied to it. So what we need to do to solve this problem is we need to do two things. We need to get everything in terms of sine, and we need to get everything in terms of t. And we've solved this type of problem before. We need to somehow replace the cos 2t over here so that it is purely in terms of sine or constants, that doesn't matter, and purely in terms of t, not 2t. So we're going to use the identity cos of 2t is identical to 1 subtract 2 sine squared t, and that will solve our issue. So I can now replace this on the left hand side. So therefore, let's substitute all that in. So we're going to have 1 subtract 2 sine squared t will be equal to 2 subtract sine t. So you see how all these skills are fitting together once again. Now let's collect like terms, and I'm going to put everything onto the right hand side so I get a nice positive value for sine squared. So I'm going to add 2 sine squared t to both sides and subtract 1. So I'm going to get 0 is going to equal 2 sine squared t. And like I said, I'm subtracting 1 from both sides. So subtract sine t and then plus 1. So I now have a quadratic in disguise, or just a quadratic, depending on how you look at it. And depending on how comfortable you are with this, you could make the substitution that you might be familiar with like this. So let big X equal sine t. It's completely up to you. I'll do that. So big X squared, subtract 2, sorry, I beg your pardon, subtract just 1 big X plus 1. So what this is telling us is this will solve for, if we solve for t, it will tell us the parameter or the value of the parameter where the line, which I've called L, and the curve C will intersect. Now, if they do not intersect, then no such t will exist. So I'm just going to move up to the top right-hand side, so we've got a bit more room to work this out. So what do we think is going to happen? If I'm trying to solve this equation and there are no solutions, what do we think we need to show? Well, it's all down to the discriminant, isn't it? If we know there are no solutions to this equation, then the discriminant must be negative. Let's see if it is. So we're going to check the discriminant now. A very powerful feature of the quadratic equation. So going back to our coefficients, we have a is obviously equal to 2, so we'll write that down first. So a is equal to 2. the value of b is, it's minus, but it's obviously -1. So b is equal to -1, I should say. And then we've got c here. Okay, so that's going to give us +1. All right. So let's evaluate the discriminant. So b squared subtract 4ac is the discriminant. And let's sub in those values. So we're going to have 2 all squared. No, that's wrong. Try that again. -1. I put the brackets around it as well, and I put the wrong number in. B squared. Okay, minus 4 lots of A, which is 2, and C, which is 1. So let's see what this value is. So that's going to give us 1 when you square -1, subtract 8, which is equal to -7, which is strictly less than 0. So that means that there are no real solutions. There are complex solutions, but no real solutions. So hence C and L do not intersect. Okay, and we've done that with the discriminant. So you remember doing that with lines and circles. You always get a quadratic, and then you show from the discriminant that there's either no points of intersection, there are 2 points of intersection, or 1 when there is a tangent. Okay, so that's one way of doing it. Now I'll show you an alternative method for this as well. You can do it in a very similar way. So just get rid of all this. So alternative. Now, just by following the same protocols we've done previously, making the trig functions the subject, we can just say that sine t, which was equation 1, which is now gone. By the way, if you're happy with that method, you can skip on to the next example if you wish. Okay, so if we make sine t the subject, that's clearly going to be equal to 1 subtract x. Okay, there's nothing to do with the second one. We're simply stuck with cos 2t is equal to y. And then we have to think of an identity that links together cos 2t and sine t. So it's quite similar to what we did in the previous lessons, previous examples. So again, we're going to use that same identity. We're going to use the identity cos of 2t is identical to 1 subtract 2 sine squared t. Now, this is really good. So the cos 2t, I can simply say, okay, great. We can swap that out straight away. So y, and remember, we lose the identity, we lose that third line because we are specifying that in this situation, sine t is equal to 1 subtract x and cos 2t is equal to y. Okay, and then we swap out the sine squared, so that's going to be minus 2 lots of 1 subtract x all squared. Simply because if you look at the first line there, we get sine squared t must be equal to 1 subtract x all squared. You've got to square the whole thing. So we now have a Cartesian equation for this. Now, this we'll call, I suppose we've used 1 and 2 already. We can call this equation A. All right, and the y equals x plus 1, which I'll just write down again. We can call that equation B. So it's still simultaneous equations, but I'm just labeling it slightly differently. Okay, now if you want to see whether those two curves intersect or not, then you simply just set them equal to each other. Now, you'll notice I've not mentioned t, as in the range of values of t at the moment, but I'll get onto that later. So if we set them equal to each other, we're going to have 1 subtract 2 lots of 1 minus x squared. 1 minus x all squared is equal to x plus 1. And we just have to expand and simplify now. So 1 subtract 2 lots of, I'm just going to open a big square bracket here, so we don't get muddled up. So it's going to be 1 subtract 2x plus x squared when you expand all that. And all of that is being multiplied by -2. So just close the square bracket, is equal to x plus 1. All right, and then we'll notice, of course, the ones on either side will cancel out. We've got 1 there gone, and that's gone as well. So just multiply through by -2 now. So we've got -2 plus 4x subtract 2x squared is going to be equal to x. Once again, I'm going to put everything on the right-hand side by adding 2x squared, subtracting 4x, and adding 2. So 0 is going to equal 2x squared, subtracting 4x, so it's going to be -3x, and then adding 2 is going to give me plus 2. So we now have a quadratic again, and we'll go back up to the right-hand side, so we've got a bit more space. So once again, let's have a look at the discriminants. We have a is equal to 2, b is equal to -3, and c is equal to +2. Right, putting all those into the discriminant. B squared minus 4ac, what do we get? Well, we get -3 all squared. Subtract 4 lots of a and c, which is 2 times 2. So this is going to give me 9. Subtract 4 times 4, which is 16, which is obviously negative, isn't it? So that's the difference between, 9 subtract 16, which of course -7, which is less than 0. And again, no real solutions. Just that point on the values of t. Obviously, if there's no real solutions, the line and the curve do not intersect whatsoever. So it doesn't matter. If for all real values of t, it doesn't matter. They don't intersect at all. So even for this small restriction, that's just a restriction on the real number line. So if they don't restrict for any real values of t, they're certainly not going to be, so if they don't intersect for any real values of t, then they're certainly not going to intersect for t values between 0 and 2 pi. Okay, so that's the alternative method for example 3. Okay, now due to limitations of space, I'm just going to do part A up in the top right-hand corner up here. Okay, you guys should have plenty of room on the page to do this. I just want to keep everything all together and visible. So it says for part A, show that all points on C, which is our parametric equations defined between 0 and 2 pi for our parameter t, satisfy that particular quadratic right here. So in order to do that, we just apply the same rationales we've done over and over again. And this is taken from an examination type question, the same format, and you can see the type of skills on display. All right, so it's a good revision exercise as well when you come back to this later. So to show that all points on C satisfy that equation, we're simply asked to find the Cartesian form. So I'm first going to go to the parametric equations, and we're going to make the trigonometric parts the subject first. Okay, so x plus 1 is going to equal sine t. That's the first thing. And That's from equation 1. From equation 2, I can see that cos 2t would be simply y subtract 3. So I'll keep that on the right-hand side. So that's going to be cos of 2t. Now, to link these two equations together, we need an identity that combines cos 2t and sine t. We've already used it several times, so we're going to use the same one again. So we know that cos of 2t is identical to 1 subtract 2 sine squared t. And this allows us to put all our ingredients together. So on the left-hand side, we can replace cos 2t simply with the y subtract 3 that we have right in front of us. So I'm going to swap these two out. And then the sine squared, I just have to square the x plus 1, and then we've got everything we need. So it's not as daunting as perhaps you thought. So we're going to have y subtract 3 equal to 1 subtract 2 lots of, now it's going to be x plus 1 all squared. Simply because if I square sine up here, that would have to square all that. Okay, so just so you're aware of that. Now, we've almost got the form we need. We just need to add 3 to both sides. So therefore, by adding 3, I get 4 subtract 2 lots of x plus 1 all squared, which is a quadratic, of course. Okay, so that's really good. Just something to bear in mind, of course, for the next bit, we're going to have to sketch this curve. Now, the curve C is not, I mean, this links to part C. It's not the quadratic defined for all real values of t. So it's probably going to be a good idea right now to figure out what the domain and range are. All right, so for the domain, we go back to equation 1 and we look at the maxima and minima, or the maximum value and the minimum value. Well, obviously, because it's sine, going back to equation 1, its sine is bounded between -1 and 1. So we simply just swap out the sine t for its minimum and maximum values to get the minimum x and the maximum x respectively. Okay, so it depends how you want to do it, of course. So this is just one way of doing it. So we know that sine t is bounded between -1 and 1, and that's fine because that's what happens when t is between 0 and 2 pi. Sine goes through one full period. Subtracting 1 from both sides, we get -2. Sine t subtract 1, 0, and obviously I can swap out the sine t subtract 1 here, so that will give me my domain. So we're going to have -2 x up to 0. So that's going to help me with the sketch in a minute. Now for the range, it's exactly the same idea. So we go to equation 2 for the range. Just reference that there. Now cos 2t, again, we've established that cos 2t is going to have exactly the same range as the values as sine t. It doesn't make any difference. The 2 is a transformation in the x direction, so the range is not affected. So it's still bounded between -1 and 1. I simply have to add 3 to all this. So adding 3 to -1 will give me 2. Add 3 to that will give me my expression for y, and then adding 3 to 1 will give me 4. So there we go. So I can now say that my range is going to be between 2 and 4. So we've got everything we need to do this sketch. So we've got my domain right here, got my range here, and we've got the shape of the curve. So I've got some space here to draw this, to do this sketch. Now, looking at the domain, it's on the left hand side, and the range is on the top half of the grid. So it's the top left quadrant that we're going to be working in. So we'll put that on here. So you might have a bit more space than me to do this. In fact, let me just start that again. It's the top left, so I can afford to move that over a little bit. It's going to be something like that. Now then, we're going to put in all the key points. Just label the axes. So there's Y. There's X. All right, now my domain is just between -2 and 0. That's good. And we also know something else about our curve. If I put my -2 here, and just looking at this curve in Cartesian form, if I set that squared part equal to 0, that gives me the equation of the mirror line, which is of course x equals -1. So I know I've got a mirror line right in the middle of my domain between -2 and 0. So that's good. And I know that the maximum value occurs along that mirror line because that's a property of a quadratic. So that's going to be at 4. So this maximum point here is going to occur when y equals 4. Also, the minimum y value we can have is at 2. So the question is, what's happening when x is -2 here and x is 0? Well, we need to find that out, don't we? So I'm just going to find out how this curve is behaving. I'm gonna guess, because the mirror line is at -1, that we're going to have the two minimum y values at -2 and 0. So let's have a look. If I substitute in x is equal to -2, then what do I get? Well, my y value is simply going to be 4 subtract 2 lots of -2 plus 1, which is of course -1, all squared, which is 4 subtract 2, which is of course 2. So it's as we'd expect. So that's going to go there. And then if I substitute in x is equal to 0 for the y-intercept, just to confirm this, we have y is going to equal 4 subtract 2 lots of 0 plus 1. Okay, which is 4 subtract 2, which is of course 2. Now, you don't really need to do both of them, just because we've got the mirror line halfway between the two. So we know that it's going to be exactly the same y value on the other side because of the symmetry. But it's just good just to check. So that's a good confirmation there. So we can now sketch this graph. So it's going to start here. It's going to go up to 4 at the mirror line. It's going to come down. So that's my curve C. Okay, and C is y is equal to 4 subtract 2 lots of x plus 1 all squared, with the limited domain of x being restricted between -2 and 0. Okay, but that's the sketch completed nonetheless. So for part C, we've already answered this in all the work we've done. The reason why C does not include all the points is simply because in the function or the curve that they've stipulated here, it includes all real numbers. Okay, so you can just say that C has the domain, which we've already established, of -2 up to and including 0. Okay, and that's only because not all real numbers. And right, so this is going to be the interesting bit, and this is quite a challenging thing to get across, and a similar type of situation came up in an exam. So I'm going to spend a bit of time explaining this last part of the question. So it says the line x plus y equals k, where k is a constant, intersects C at two distinct points. So for part D, we know that k is a constant. That's fine. If I just make y the subject, that tells a bit more information about the nature of this straight line. So if x plus y is equal to k, then we know that y must equal k subtract x. And that tells us two things. That tells us the y-intercept is going to be at this particular value of k, and the gradient, which we call m, is -1. So it's a slope of -1. Right. So I'm going to have a go at just sort of sketching this straight line graph, and we're going to move it around a little bit. So don't sketch this just yet if you're watching the video. Just hold back and wait until the end of this example before you draw it in. So I'm going to draw this line in. Now, trying to get this gradient of -1. I'm just going to put it up here for now. So like I said, don't draw it in just yet. And just bear in mind that wherever this straight line graph that I've just drawn here, wherever it crosses the y-axis, that's the value of k. All right, so I can still label it. This is going to be y is equal to k subtract x. Now, because we don't know the value of k, this is indeed maneuverable. Okay, so I can move this up and down as I wish. All right. So what do we need to do? We need to find two distinct points. I'll just move this out of the way. Two distinct points so that the curve and the line intersect. Well, this is where your alarm bell should start ringing. If two distinct points, that is telling us something about the discriminant, isn't it? So that is screaming at you that the discriminant b squared minus 4ac has to be strictly positive. Okay, that's what that's telling you. And that's when we substitute one curve into the other straight line. Right, so how do we do that? Well, we could do this one of two ways. I'm going to go back to the parametric equations, and I'm going to do it as follows. So given x plus y is equal to k, what that means is that my x value, which is going to be sine t subtract 1, so I'll sub that in first. So that implies that sine of t subtract 1, which I'm just going to show you again. This corresponds to my x part here from equation 1 up here. Okay, now let's do this. Let's do the next bit. So that's x plus y. So I've got to add the y part. Now y is defined as 3 plus cos 2t. So let's put that in. Okay, so again, just so you know, these correspond. So that corresponds with that one. Okay, if I add those together, that's going to equal k, which is a constant. Okay. Right, now we can use, we can tidy it up a bit. So we've got sine t plus 2 plus, now just for the sake of room, I can replace the cos 2t with 1 minus 2 sine squared t, which we've done several times already, which you may have anticipated was going to happen, is equal to k. And then I can create a quadratic, a trigonometric quadratic in terms of sine. Now, putting all this together and rearranging, we're going to get 2 sine squared t. Okay, I'm just putting all this together on one side. Subtract sine t. Okay, and then just putting the numbers together, the constants. I've got +3 on the left-hand side, and combining that with the k on the right-hand side, that's going to give me plus k subtract 3 must all equal 0. Now, I've perhaps missed a step out there. I'll leave that for you guys just to check that you agree with that. So I now have a quadratic in disguise. Okay, although it's not a very good disguise because we've done so many of these. So my a value is, of course, 2. My b value is going to be -1, and my c value is going to be k subtract 3. Now, just to create a bit more space, I'm just going to remove some of this working from the top right-hand corner, or the domain and range, which we've done now. So I'll just get rid of that. Again, you've got plenty of space on your page to do this. So I'm just going to, so this is going to go all the way up here. Continued. So let's write down what our A, B, and C are. So A is going to be 2. B is going to be -1. And C is going to equal K subtract 3. And we know the discriminant has to be positive because it has to intersect twice. So B squared subtract 4AC has to be positive. Just partition that off. So that means that -1 squared subtract 4 lots of 2. I've not left myself enough space there. I will have to drop down a little bit further. So -1 squared subtract 4 lots of 2 multiplied by k subtract 3 is positive. Now 1 subtract 8 multiplied by k subtract 3 is greater than 0. I'm going to move all that over to the other side. So we're going to have 1 is greater than 8 lots of k subtract 3. So 1 is greater than 8k subtract 24. Add 24 to both sides and divide by 8. So we have 25 over 8. And k has to be strictly less than that. Now, this is almost where we want to be. We've got a restriction on k. Now, remember, k is the y-intercept of my straight line. Now, if you're not sure what 25 over 8 actually looks like, this is it's actually quite simple. It's about, or it is in fact 3.125. Okay, if you just do it on your calculator. So that means that the y-intercept, the upper limit is 25 over 8 or 3.125. And I would forgive you for thinking, okay, well, that's the answer, isn't it? Okay, as long as k is less than 3.125, we're in business. But you'd be wrong. Now, I can explain why you'd be wrong just using this fantastic graph that we've drawn over here on the right-hand side at the bottom. So I'm just going to clear a bit more space because we may need a bit more space just to argue this point. And I'll just write on that equation again. So I've just rubbed it off. So this is y is equal to k subtract x. Now, what we've established is, I'm just going to move it into position. So that upper limit is about there. And what that means is where this graph crosses the y-axis about here is at 3.125, which isn't a bad shout looking at the way I've drawn the graph. Okay, it's not a bad diagram really. Now that would give you a tangent, so that would give you a single point of contact on the curve right there. Okay, which is why it's a strictly less than situation. Now you'll notice if I move this line down, so if I reduce my value of k, from that point, I don't have one point of contact anymore, I have two. Okay, so if I take that point, for example, I've got a point of contact here and a point of contact here. And if this was for all real values of x, as it was stated in part C, where we were given no restrictions at all on x, it could be any real number, that would be the end of it. We could just say k is strictly less than 25/8. But we can't, because we have a restriction on our domain. We're only allowed to put in x values between -2 and 0. And you can see that clearly from the graph we've drawn here and from all the work we've done already. So what we have to do is we have to see what happens if we move this line a bit further down. So we have to have 2 points of intersection. Now, 2 points of intersection will stop the very moment my y-intercept drops below 2, because the curve ends. Okay, the curve is not defined below the point 0, 2. From that point onwards, there is just going to be either one point of intersection, which you can see right there as an example, or there's going to be no points of intersection, because if I carry this further on, it's going to go down and down and down, one point of intersection all the way, and then until I get to this point here, there's going to be nothing. So where is my limit? Well, my limit occurs the very moment my y-intercept drops below 2. So that's the final answer. So the restriction on k, I'll just write in here. So there are two distinct points of intersection when, and I hope I've argued this convincingly, k is bound between 25/8, which is the upper bound, which is where you have that tangent that we saw earlier, but also when k is greater than 2. Okay, and that's from the graph. That's why they ask you to sketch the curve first. So what I suggest you do is practice several of these questions. They're quite challenging. Get a few of them under your belt, and then you'll be very well prepared for any potential exam situations. Okay, so thank you very much.